Hello viewers, I am Alankar Datta, a graduate student in the Department of Physics at the Indian Institute of Science in Bangalore. Today, I am going to talk about our recent work on modeling the large-scale structure and distribution of gas that forms a circumgalactic medium. The circumgalactic medium, or CGM for short, is a diffuse gaseous medium extending well beyond the galactic disk. CGM models can be employed to predict the gas properties like its temperature and density, and also generate synthetic observables which can then be compared and validated against actual observations. Here are a few examples of such CGM models from literature. As you can see, most of these models are simple radial profiles. They are often developed with the aim of just explaining a limited set of observables. However, now with the growing wealth of diverse multi-wavelength CGM observations, radial profiles are just too simple to self-consistently explain all the different observations. Moving beyond radial profiles, in this work, we propose a probabilistic approach towards modeling the multiphase CGM. Our probabilistic CGM models generate synthetic observables that are in better compliance with different multi-wavelength observations. To start with, we generalize the isothermal and isentropic CGM models proposed by Faerman et al. 2017 and 2020. Let us now briefly look at our probabilistic approach. Specifically, we are using log-normal probability distribution functions, or PDFs for short, to model the multiphase gas in the CGM. This is inspired from turbulent simulations. Imagine a radial shell in a spherical CGM, as you can see in this cartoon. Unlike previous models, in a probabilistic prescription, this gas will not have a unique temperature or density, but rather a spread. The gas in every shell has multiple values randomly sampled from an underlying log-normal PDF. Such a randomness is due to turbulence collectively caused by a myriad of events. This includes outflows, infalling satellite galaxies and mergers, and mixing due to hydrodynamic instabilities. In a typical CGM, most of the volume is occupied by the hot gas at virial temperature, which is about a million Kelvin for Milky Way-like galaxies. However, the CGM is quite non-uniform and is virtually littered with warm and cold gases. This can be seen in one of the simulated halos here on the right, which is taken from the Illustris TNG50 cosmological simulation. Coming back to the spherical shell, the hot gas in the CGM therefore has a distribution as seen by this red curve. Part of this log-normal PDF is, however, thermally unstable. It quickly cools radiatively to populate another log-normal PDF at a lower temperature, forming warm gas. This you can see by this blue curve in the figure. Such a spread, as I was alluding to earlier, can in principle be in both density and temperature. Therefore, we use two-dimensional log-normal PDFs to describe the entire CGM as a three-phase one-zone model. Here's what I mean by this. In this figure, in the color map, we are showing the phase space distribution of gas from one of the Milky Way-like halos from the Illustris TNG50 cosmological simulation. The black ellipses are the three log-normal PDFs corresponding to the three phases of gas in the CGM, namely the hot, the warm, and the cold. The total of these three PDFs is shown by the dashed white contours. As you can see, especially in the marginalized PDFs at the top and right panels, our log-normal CGM model is in quite a good agreement with the Illustris TNG data. Next, we generate different synthetic observables from our models to see how well we do when compared to multi-wavelength CGM observation. One of the several observables that we consider is the quasar absorption spectra. The way it works is that we have a foreground galaxy in front of a quasar, which is a bright point source of continuum emission. The CGM of the foreground galaxy, depending on its composition and ionization state, imprints absorption lines on the otherwise continuous quasar spectra. From this, at different projected distances b, we can infer the column density of different ions along the line of sight. For many such quasar galaxy pairs, we can observe the column density of different ions, for example oxygen 6 and magnesium 2. On the screen, you can see the column density of oxygen 6 ion in blue, which traces the warm gas around 100,000 Kelvin, and magnesium 2 ion in red, which traces the older phase of the CGM, which is around 10,000 Kelvin. The lines you see are predictions from our probabilistic CGM model. While we are able to explain the baseline trend, we are currently working on improving our model to account for the special features and discreteness of gas at different phases in the CGM. This would enable us to better explain the large scatter in these column densities that we see in the observation. A multiphase CGM leaves its signature in observables spanning a wide range in the electromagnetic spectrum. For instance, we have the soft X-ray spectra and emission measure from E Rosetta. In radio, the Milky Way CGM contributes significantly to the total dispersion measure. The idea here is, therefore, to build a comprehensive library of different CGM models. Some of these models are along the column of this table taken from our paper. We compare synthetic observables generated from these models covering a wide range in the electromagnetic spectrum, which are along the different rows. We are in the process of compiling an extended library of models and observables that would enable us to validate or falsify certain models. We hope to constrain the CGM properties with much greater confidence than ever before. By combining observations across different wavelengths and comparing them to our models, we can gain a better understanding of the complex multiphase nature of the CGM and its role in galaxy evolution. I would like to take this opportunity to tell my viewers about our newly developed tool called AstroPlasma. It is a powerful tool that uses pre-computed cloudy tables to generate ionization conditions in the plasma. This provides a computationally efficient and a fast way to calculate ionization needed for producing synthetic observables. We have got big plans for AstroPlasma, and we intend to expand these capabilities and use case scenarios to cater to the needs of a wider community. I'm really interested to hear your thoughts and ideas on how you intend to use AstroPlasma, so please leave your suggestions in the comments below. If you'd like to check AstroPlasma for yourself, head over to our GitHub repository. I'll link it in the description. Alright then, that's it for the video. If you have made it this far, thank you so much for watching and for your interest in our work. I really hope you found this interesting, and I would love to hear your thoughts and engage in discussions about our work. Please feel free to reach out to me anytime. That's it for now. Until next time, take care.